Welcome back. We were discussing in Fundamental of Electronics about the power amplifiers. Previous two lecture we discussed on two important types of power amplifier, that is A and B or AB type of power amplifiers. We will discuss here what is class C amplifier and its characteristic. Class C amplifier conduction will be less than 180 degree for the input AC signal. We saw that in class A, the conduction was for 360 degree. For class B amplifier, the conduction process lies between 0 to 180 degree. But for class C amplifier, the conduction will be less than 180 degree. These amplifiers are highly efficient as compared to class A or class B amplifier. However, they are not suitable for audio or linear applications. They are primarily used in radio frequency circuits and they use resonant circuits for distortion. Resonant circuits are basically the LC networks which are used in class C amplifiers. They are biased below the cutoff, so the transistor will be off for most of the input AC cycle. The short conduction time makes the transistor on for only a small portion of the positive AC supply. The nonlinear amplification process in class C amplifier leads the output to be distorted. It requires the tuned circuit, which is basically the resonant circuit, to get the sinusoidal output. These type of amplifiers have high efficiency up to 90%. If you remember, in class A amplifier, the efficiency maximum was 25%. The class B amplifier, the maximum efficiency was around 78%, whereas class C amplifier will have the efficiency close to 90%. And hence they are ideal for high power radio frequency transmission. Some of the common applications of class C amplifiers are basically used in RF transmitters, whether it is AM or FM broadcasting, the communication system. It is used in oscillators for generating the stable RF signals and the modulators for controlling the high frequency signals with the low frequency input. If we talk about the circuit and the waveform of class C amplifiers, so let us take the example of a resistive load, which is only for the conceptual understanding. However, it is impractical for the real practical example. The waveform behavior is as such where the base voltage is biased below the cutoff with negative base voltage VB. So we are basically giving the supply of the base to be voltage of the base VB, and the transistor is turned on when the input voltage exceeds the base emitter threshold voltage. So the input voltage that is given on the transistor should exceed the threshold voltage of the base emitter. So base emitter potential drop of 0.7 volt, it has to exceed, then only the transistor will conduct. The collector current will flow briefly in each cycle when the conduction process takes place. And the load line analysis, if we do, then when the transistor is fully on, then the current reaches to the maximum, that is the saturation current. And when the transistor is off, the collector voltage will be also at its peak. So this is the load line where we draw the collector current and collector to emitter voltage. The maximum collector current which we get at the saturation is IC saturation, and the maximum voltage that we get is BC saturation. So this is what we got when the transistor is fully on, and when the transistor is fully off, we will get that current. So the input voltage has to be exceed the threshold voltage, and then the transistor will conduct for the base voltage plus the base emitter voltage. So very small duration of the collector current we will get at the output. The power dissipation, if we talk about, then the collector current pulses which is formed due to the transistor conducting only during short pulses in each input cycle. So if we see the input of the AC cycle in the voltage input, we get the collector current. This collector current is present for each half cycle of the input for a very small duration, that is from less than 180 degree. The time between these pulses forms the period T of the AC input voltage. So this is the time which is between the two pulses. So that is basically the time period. If we talk about the voltage and the current during this conduction process, then during the conduction, the collector current will reach the collector maximum saturation current. So this is the maximum current of the collector, and the voltage will be also reaching the maximum value, that is the collector to emitter saturation voltage. So the voltage is reaching to its maximum and collector is also reaching to its maximum during the conduction. The power which is dissipated or the on time is basically the product of collector current and collector to emitter voltage at the saturation point. And this average value, if you want to calculate, then the power dissipation has to be multiplied with the duty cycle. So duty cycle is given by T on by T, because the T is the total period and T on is the time for which the transistor is in on. So here we can see that lower the average power dissipation, making the class C amplifier to be highly efficient. So if the duty cycle is less or lower, then average power dissipation will be also less, and we will get highly efficiency of the class C amplifiers. So if we talk about the loading effect of this class C amplifier, then it is unsuitable for linear application. The output does not resemble the input signal. So the input signal that we give in this amplifier is basically sinusoidal, but the output that we get is not sinusoidal. Hence, it does not suitable for the linear applications. Class C amplifiers are used with parallel resonant circuit, which are known as the tank circuit. So here you have the parallel combination of inductor and capacitor, which is used as the parallel resonant circuit or the tank circuit to get the sinusoidal waveform. So the tank circuit will save the output in the sinusoidal waveform. So the output that we get now will be sinusoidal because of this tank circuit which we use it. So the output current pulse, which is less than 180 degree, but the output voltage what we get is sinusoidal because of the tank circuit or the parallel LC network. The resonant frequency of this tank circuit is given by 1 by 2 pi under root LC, and at this frequency the impedance of the tank circuit is highest, resulting in a large voltage gain. So here the circuit will be entirely resistive in nature, so the impedance will be highest and we will get the highest voltage gain. So the question is how the tank circuit is producing the sinusoidal wave output. So step by step we try to understand this. So first we need to initiate the oscillation. A short pulse of collector current will charge the capacitor to approximately the voltage of the supply, which is plus VCC. Now the oscillation will start because the capacitor will discharge and the inductor will charge. Hence the magnetic field will build up. So capacitor and inductor will charge and discharge alternatively, and there will be magnetic field established because of the inductor present charge. So the inductor magnetic field will collapse and the capacitor will recharge in the opposite polarity. So once the inductor start discharging, the capacitor will start charging and one complete cycle of oscillation will form. Now the sustaining the oscillation will be there in the network because the resistance within the tank circuit will lead to energy dissipation. So the resistance is basically used in the circuit because you have to dissipate the power which is present in the LC network. This dissipation will cause the oscillation to gradually diminish over time. So when there is oscillations, then it will be dissipating in the resistor the energy and the oscillation will die out. So each pulse of the collector current will act as a repletioning forces, and these pulses will inject the energy back into the circuit, counteracting the losses. So whatever the losses is taking place in the resistance, these losses will be injected back into the circuit with the help of the collector current. The balance, which will be because of the energy loss and the re-energization process, will maintain stably and oscillation will continue. This dynamic is crucial for consistent performance in oscillator design. So the LC network, which is basically the tank circuit, parallel resonant circuit, along with the resistor which act as energy dissipating parameter. So together it will sustain the oscillation. Here we can see in the circuit what is actually happening. So we have the capacitor C1 in the circuit, and the transistor here Q1 is basically conducting, and the capacitor current is approximately short. So the capacitor C1 is charging to the potential plus VCC at the input peak when the transistor is conducting. Now, if the transistor is off, then the energy which is present in the capacitor C1 will be discharged to 0 volt. Again, when the transistor remains off, the energy which is present in the inductor will be recharging the capacitor C1 in opposite direction. So, transistor is still remaining off, the capacitor will discharge to 0 volt and the inductor will again recharge to C1. So, this exchange of energy between the inductor and the capacitor will result in the output which is sinusoidal in nature. So, we will be getting a sinusoidal output because of the tank circuit. There is frequency multiplication in the class C amplifier. Because the tank circuit is tuned to the fundamental frequency, it will oscillate at the input signal frequency. If the tank circuit is tuned to the second harmonic, then the oscillation will be doubled than the input frequency, and higher harmonics if we give, then we can achieve further frequency multiplication. So here we can see the oscillation which gradually die out due to the energy losses, and the capacitor pulses are a very short duration. So we get the output which is sinusoidal oscillations, and the frequency multiplication can be there or it can be doubled if we give the harmonics of twice the fundamental frequency. So what are the key takeaways from this discussion that we have done till now is that class C amplifiers are highly efficient, about 90%. Than class A or class B amplifier, but they are inherently non-linear in nature. The tank circuit, which is the parallel NC network, filters and convert the pulse current into sinusoidal output. So output we are getting sinusoidal because of the tank circuit, and frequency multiplication can be achieved by tuning the tank circuit to harmonic frequency. So if we estimate what is the maximum output power and efficiency, and the tank circuit is basically having the voltage peak at twice the supply voltage to VCC, with the maximum output being given as the prod square of the RMS voltage by RC. This is the fundamental equation, and this RMS voltage can be written as a root 2 times the maximum voltage square. In that case, we get 0.5 VCC square by RC, where this resistor is basically equivalent parallel resistance of the collector tank circuit at resonance. Then the total power which is supplied to the amplifier, if we want to calculate, that is basically the output power plus the energy which is dissipated average value, and hence we can compute the efficiency as total power output by total power input. So input is again output plus the losses. So if the output is very high than the losses, then the efficiency will be close to 1, which is 100%. So class C amplifiers are highly efficient because the losses is less here. So there is a clamping action in class C amplifier. So clamping circuit which is used in class C amplifier, and it will bias the transistor at the negative voltage level. So the transistor will conduct only at the positive peak of the input cycle. So when we are giving this signal, which is a AC signal, and the transistor we are using with the LC network, so if some sort of biasing we are giving with the help of the biasing network, and it will conduct the transistor only at the positive cycle. So here you will be getting the conduction. So the transistor has to turn on during the positive cycle and off during the negative cycle of the input. That is a biasing effect. What is the working of the clamping circuit? So let us try to understand. So the capacitor C1, so here you have the capacitor C1, which is basically charging during the positive peak, and the input signal will go positive. So the input signal, when it is going positive, the capacitor is charging, and it is charges to a potential Vp minus 0.7. This minus 0.7 is because of threshold voltage and through the base emitter diode. So here the transistor is acting as a diode now, which is at the output. This establishes a negative average DC voltage at the transistor base. So transistor base, whatever potential we are getting is minus Vp, and it has to maintain the charge because the time constant of the RC network is large enough. So the capacitor will discharge very slowly because the time constant, which is product of RC, is much greater than the period of the input signal. And the average charge on the capacitor remain close to Vp minus 0.7 volts. So this is the average charge on the capacitor. So here we have the cycle of the AC, which is basically charging the capacitor to a potential Vp minus 0.7, which is due to the base emitter threshold drop. And you have to establish the base voltage. The DC value of V in has to be 0 volt. Then the transistor base will be negative side of C1. So base voltage will be now negative of Vp minus 0.7. And the AC input signal is superimposed to this DC level, shifting the voltage up and down accordingly. So when we are giving the input AC cycle to this capacitor in the positive and negative half cycle, only in the positive half cycle it will conduct, negative half cycle it will not conduct. So what conduction process that we get is only for small time period in the positive half cycle. So the transistor will conduct only at the positive peak. So here only the transistor conduction is taking place when the input signal is reaching its peak base voltage, momentarily exceeding 0.7 volt. So the forward biasing of the base emitter junction will allow the transistor to conduct briefly. So the time period when we are giving for the AC signal, here we have the base, and due to this capacitor we are able to conduct in a very small zone of the positive cycle, which is the base emitter, and it is at the positive. In the negative we have the negative of minus Vp minus 0.7 volt. So this complete the discussion on our amplifiers. So we have discussed 3 important types of power amplifiers in very detail. Next lecture we will start with field effect transistor. Thank you for now.